I'm going to try to get through the rest of chapter 1, and if I can, then we're going to have a test next week, maybe on Friday. I have a follow-up appointment with my surgeon on Thursday, so maybe I'll be released and I can come back on Friday. So that's what the plan's going to be. If I can't be there, then I'll see if Amy can give the test. So to review what we talked about in the last video, we talked about matter and energy, everything being one of the two or a combination thereof. Matter using energy, energy using matter, matter creating energy, energy creating matter. So we talked about that. We talked about matter being a primary characteristic of matter being that it has mass and occupies space. We made a distinction between mass, matter, and weight. They're not the same thing, but any type of matter is going to be made of atoms and molecules. Molecules we're going to talk about in the section after next. We're going to talk about what atoms are, how they combine. We're going to talk about all that later on. So just for now, you need to know that all matter is made up of atoms. Even matter that you can't see is made up of atoms. For example, the air that you breathe is oxygen and a variety of other types of gases. It's still matter, even though you can't see it and you can't feel it unless the wind is blowing. So we talk about weight and what weight is and its gravitational effect on a mass, and it's not the same thing as matter itself or mass itself. We have a tendency to draw an equivalence between the two, but they're not the same thing. And we looked at why they're not the same thing. We took a look at a water analogy. You could have water in 3 different states. You could have it in gaseous, solid, or liquid state, and it's still the same quantity of matter, but the weights are totally different. We also took a look at a planetary example. Then we went into energy, and the definition of energy is just the ability to do work. And we walked through the different types of energy that we're most interested in medical imaging. Potential energy is what we call KVP. It's potential energy is potential difference between the cathode end of the X-ray tube and the anode end of the X-ray tube. And it is the definition of potential energy is just stored energy. It's unrealized. It's the ability to do work even if work has not taken place. So once we apply the KVP, then our electrons travel across the tube and they become kinetic. Kinetic is the energy of motion. Chemical energy is the energy that we find in digestion or in batteries. And in medical imaging, we use batteries to power some of our portable machinery and a number of different things. We talked about electric energy, and electric energy is just the energy that you get with the movement of electrons. And we're going to use electric energy, and we're going to manipulate electric energy and cause it to have different power levels, and in that we can create x-rays. So with the electricity that's just coming out of the wall, we can't really create any x-rays that would be in a range that would be beneficial to us. So we have to manipulate it. Talk about thermal energy, and that's energy on the molecular level. You rub your hands together and they get hot. But where we see thermal energy is in the X-ray tube. The main thing that we create is heat, because anytime you send electrons through a wire, through any kind of circuit, remember you create 2 things. One is a magnetic field, and we'll talk extensively about that later in the semester, but the other thing is heat. And you can see the heat in applications like your toaster, your oven, or anything like that. So nuclear energy, certainly we can get nuclear energy from a nuclear power plant. We're also going to see nuclear energy later in the curriculum whenever we talk about nuclear medicine. And that is just the energy from the nucleus of the atom in the breakdown of unstable atoms. And then we talked about electromagnetic energy, and that's certainly what we're most interested in diagnostic x-rays. So electromagnetic energy behaves like light in a lot of different ways, and that is, again, we're going to talk about this later in the semester, but it travels in waves, it has specific frequencies, and it incorporates everything from microwave radiation, which you eat your food up with, all the way up to x-rays and gamma rays. So it encompasses visible light, X-rays, gamma rays, and radio frequency and things like microwaves. So electromagnetic radiation is what we're trying to create. And in the X-ray tube, what we create primarily is heat. Secondarily is light. You just can't see the light because of all the stuff that surrounds the X-ray tube. And we'll get into all that later on in the semester. And then we create a small, very small amount of X-rays. So then we talked about radiation, what radiation is, and that's just transfer of energy from one place to another, and a lot of different types of radiation. Not all radiation is harmful, some is. The type that we're going to focus on that is harmful is ionizing radiation. Ionizing radiation is energy with a high enough energy level to eject an orbital electron from an atom. In doing so, you ionize the atom. Ion just means charged particle. So the electron that you eject from the atom becomes, free and unbound to anything. So it's a charged particle. It's a negative charge. But at the same time, the atom itself also becomes a charged particle. It's positively charged, which means you have two charged particles, which means you have an ion pair. So ionizing radiation creates ion pairs. Sources of electromagnetic radiation we looked at on page 6. Sources of ionizing radiation we looked at on page 6. But largely, the largest portion of ionizing radiation comes from diagnostic, but we get X-rays from almost everything. So we've got internally deposited radionuclides, carbon-14, we'll talk about that a little bit later, I think maybe in the next section. We've got building materials that give us things like radon, and then we've got medical applications, which account for a large part of the man-made radiation, the largest part of the man-made radiation. But we've also got things like smoke detectors and things like that give us a little bit of radiation as well. So ionizing radiation comes at us from a lot of different directions. It's important to understand that ionizing radiation has always existed. And so the discovery of X-rays, which is where we're going next, was just that. It was discovery of something that we didn't really understand at the time. So a lot of people were doing experiments with electricity, and I want to fast forward to some links that I dare not open just because it seems like when I try to open it, that it takes me away from the PowerPoint. I can't get back into the PowerPoint. So a lot of different people were experimenting with electricity to try to figure out exactly what it was. They knew that we could use electricity in certain applications, just weren't real sure what it was. So they're doing a lot of experiments. There's some evidence that Nikola Tesla actually beat the guy that we're about to talk about, Wilhelm Conrad Röntgen, in discovery of X-rays. So there's some evidence that Tesla was working on it as well, but he just didn't identify it and study it and describe it before Röntgen did. So on November 8th, 1895, this German guy, Wilhelm Conrad Röntgen, that's not him, but that's a representation of him, was experimenting with a Crooks tube, which is kind of what you're seeing there. It's a very early version of what would become X-ray tube. After a lot of refinements, we had much better X-ray tubes. But what he was looking for was exactly what electricity was. So what you see in this Crooks tube are the basic components of an X-ray tube, really. You've got a filament, you've got a plate. So you've got a cathode where you would have electrons creating a space charge, thermionic emissions. And you can send the electrons across the tube to interact on this anode, and the gap in between would prevent the electrons from going across before you were ready for them to do so. Now, the videos that were posted on the next page you can see sort of what it was that they were doing. And I'll link these in the description so that you can see them. I think at least two of them they're recorded by people from England, so you just have to understand the accent and pay attention to what's going on there. But essentially what Rankin did was he studied it a while he could visualize what was going on. And then he thought to himself, what would happen if I were to take my Crooks tube and completely cover it with something that would prevent the light from the filament, the heating of the filament, from escaping from the Crooks tube? What would happen then? So he covered the thing up completely so that no light would escape. And what happened was that when he energized the Crooks tube, he saw this compound that was very common in laboratories at the time. It was called barium platinocyanide, but it was not right there with the Crooks tube. It was a little distance in between the Crooks tube and this barium platinocyanide. And what he noticed was the barium platinocyanide, whenever the Crooks tube was energized, would start to glow. All right, so he knew that something was getting out of his Crooks tube, even though the tube itself was darkened to the point that nothing else, no light was getting out of it. So some sort of electromagnetic radiation was getting out of it, and it was stimulating this barium platinocyanide and making it glow. That's a property we call fluorescence. Fluorescence just means glow in response to a stimulus. So he saw the barium platinocyanide glow. And he knew he had something, he just didn't know what it was. So he called it X-light, X being the unknown. So he called it X-light. He locked himself in his basement essentially for 2 weeks and studied this thing extensively until he learned the basic attributes of how X-rays behave. And we still teach that today. So what we have in X-rays are a type of light that you can't really see that will penetrate, obviously through the paper, but it can also interact with other substances and cause them to glow. So his wife came down and they took an X-ray of her hand. So this is the first known X-ray of human anatomy. And whenever she saw this X-ray, she said, well, I've seen my own death, because she could see the bones in her hand. So there's a number of things that we can get from this particular image of her hand. A lot of different things that I'm sure that he didn't really describe at the time, but what we can see is bone. So what that means is that X-rays can penetrate some things, and they have a hard time penetrating other things. So they have a hard time penetrating the bones, but you can still see the bones underneath the skin. They penetrate completely through the skin. Also, though, it has a harder time penetrating through thicker things. What he didn't know was that you see this ring here. That ring is probably completely made of gold or something that has a property that we refer to as radiopaque. So radiopaque means X-rays don't go through it well. Radiolucent means that X-rays go through it easily. So the skin is radiolucent, the ring is radiopaque. So what we see in rings is that the metal is very radiopaque and the X-rays don't go through it very well. But what else we see is that if you have a true diamond inside your ring, inside the setting in your ring, X-rays will go through that quite easily, because carbon is all a diamond is. And carbon is basically what we're made of. And if X-rays go through us, then it'll go through the carbon in the ring as well. You might be able to visualize the stone a little bit, but if it stands out like what you're seeing right here, that's not truly not likely truly a diamond, but it's maybe cubic zirconia or whatever. So he locked himself in his room. He wound up getting the Nobel Prize later that year for this discovery of X-rays. Again, it was a discovery. It was not an invention. The equipment had to be invented so that he could make the observation and the discovery of X-rays. But we've been X-rayed since the dawn of time. We get X-rays from outer space, from the stars. We get X-rays from terrestrial sources as well. So he called it X-light, and he didn't really know what to do with it. He made that one image, but that was pretty much it. So where to go with it from here? So at the onset, we had two different things that were being developed, and that was diagnostic radiography and fluoroscopy. In both cases, the images took a long time and they weren't very good. And so what resulted from that were a lot of radiation burns. So if you look on page 8 of your textbook, at the top of the page, you see Mrs. Rinkin's hand. But at the bottom of the page, you see what is suspected to be in the first diagnostic image of a broken bone. So this kid was outside playing around, fell down, broke his arm. And they brought him in, sat him in this chair, and everybody in the room was right there with an energized Crooks tube, which eventually became, X-ray tube. So everybody was being exposed to the radiation at the time, not just the kid's arm, but everybody's entire body. So it was an extremely high dose. So we didn't really know what was going on with the X-rays, and what that resulted in were radiation burns. If you look at the top of page 9, you see an image where Thomas Edison is working with a fluoroscope. So his lab assistant, who was a very close friend of his hand is on top of a box where a fluoroscope or an X-ray tube is inside of that box. So fluoroscopy, means moving X-rays. So this looks just like a wooden box. It might have been a metal box, but it looks like a wooden box. So both his lab assistant and Edison himself were getting exposed to radiation from head to toe if that was a wooden box, because X-rays were just going all over the place. So that resulted in radiation burns. His assistant, Clarence Daly, actually died from radiation burns. That caused Edison to pull up stops and decide he didn't want to deal with X-rays anymore. So it was dangerous. First medical X-ray. So in order to improve the images and also to reduce the patient dose, a number of different things had to happen. So we had to have better generators, and those came about very early on with a Snooks top generator in 1907. And when we're talking about generators, we're really talking about transformers. And I talked about transformers in lecture chapter 1.2 or 1.1, whatever it was. So we really manipulate the electricity. We don't really generate the electricity. The electricity comes to us through the power lines. So we got better generators. We got better X-ray tubes. Understanding the generators, really transformers. They generate high voltage, but they don't really generate the electricity. So then what was developed next were the use of intensifying screens. So intensifying screens took what Rinkin observed with a barium platinocyanide and used that to create the image. So what we had was an X-ray film, which you really can't really relate to because a lot of y'all have never seen X-ray film. But X-ray film, what it is a polyester base with some goo smeared on it. And that goo is made out of a lot of stuff, but the active ingredient is silver. So when silver oxidizes, it turns black. The more it oxidizes, the blacker it becomes. So you smear this goo on this polyester base and you expose it to X-rays or light, and it immediately turns a darker color. So if it didn't really matter if it was X-rays or light, then what we could do is take that X-ray film and put it under what we refer to as an intensifying screen, The intensifying screen, whenever it was exposed to x-rays, would glow, and then that would expose x-ray film, allowing us to cut back on our radiation dose quite a bit. So somebody else came along and said, well, what if we doubled that? What if we put goo on both sides of the polyester and used 2 intensifying screens? Could we cut the radiation dose down even more? And the answer is yes. So they cut the radiation dose down by maybe 50 times using the intensifying screens, and then doubled that, cut it down by maybe 100 times by using double emulsion films. Then William Rollins was a dentist that came along, and he was smart enough to realize that the x-ray tube is creating x-rays, and the x-rays go off in all different directions. So file this away. This is a word that you're going to need to know. And when x-rays are created, they're created in a way that is kind of like dropping a bowling ball into a mud puddle. They go off in all directions with equal intensity, and that's what we call isotropic emissions. Isotropic emissions means equal intensity in all different directions. So Rollins realized that we don't need that. We just need the portion of the x-ray beam that's going to strike the patient. So he took small pieces of lead. Lead is hard for x-rays to get through, and he cut small holes in it. He's a dentist. So he took that and he wrapped it around the x-ray tube, or wrapped it around the patient's head in a way that it would block the x-rays from getting to anything except for the tooth that he wanted to see, or the teeth that he wanted to see. So that's what we refer to as beam restriction. Beam restriction eventually became law. And you can't make an x-ray beam legally to expose a patient with unless you've got beam restriction inside of a protective housing. And we'll talk about all that later in the semester. So that's beam restriction. Collimation is what we call it now. And then filtration. What he realized is not all x-rays are going to penetrate through the patient. So the ones that penetrate the most are the highest energy x-ray photons. So if he were to put something to absorb those low energy photons that weren't going to do anything except for absorb inside of the patient, then he could reduce the radiation dose to the patient. They're not going to make it to the x-rays anyway. Very low quality x-ray photons, not going to make it to the image receptor or to the film and expose the film. It's just going to be absorbed inside the patient. So he invented 2 things to cut radiation dose back to the patient, and that is filtration and beam restriction. Filtration removes low energy photons, low quality photons that wouldn't make it to the image receptor anyway, and just add to the patient dose. That's filtration. He removed those, and then he limited the exposure to the anatomy of interest, and that is beam restriction. So intensifying screens, I already talked about that. Double emulsion, already talked about that. Significance of filtration, already talked about that. So with the generators, with the better generators, what that enabled us to do is thinking back to the Rollins thing with the low energy photons, X-ray photons, photon being a piece of electromagnetic radiation. Talk about that later in the semester too. If we could create X-rays with higher, more penetrating power, then that would be a better quality X-ray beam, and the patient dose would come down even more. So that's how the generators or the transformers came into play. So image improvement, what we need to see, okay, so this is a little bit advanced for now, but just file this stuff away. So what we need to see in order to visualize an X-ray and visualize anatomy of interest is we need to see contrast and density. So what you see in contrast is difference. So the lettering here is very dark, and that would be on an X-ray image an indication of a very high density. All this area out here is very light, so that's what we would refer to as low density. So contrast is the difference in those densities. So very black images are high density, very light images, very white images would be low density, and contrast is the difference between those 2 things. So what we need then is a balance between those things. So we have to have contrast, generally speaking, to be good, and we also need the density to be good as well. So beam restriction originally helped with that. Really, our computer algorithms are the things that control our contrast and density. Now, there are some things that we can do to affect that. Certainly, beam restriction being one of those things, but grids also are some of those things as well. We're going to talk extensively about grids, especially next semester. Amy's going to get to some of it this semester. But when X-rays penetrate through a patient, three fundamental things, there's really four, but three fundamental things are going to happen. Either the X-ray is going to enter the patient, it's going to go into the patient, it's going to stop. That's what we refer to as photoelectric absorption. Your patient dose, or your patient absorbs all of that dose. You get an interaction where the patient completely absorbs that X-ray photon. Possibly the X-ray photon can go through the patient without touching anything and just hit the image receptor and add density to the image receptor. And the third option is somewhere in between. So the X-ray photon enters the patient's body, it hits something, and it partially absorbs and it scatters off into a different direction. And that's what we call scatter radiation. Scatter radiation adds to image density, but it's not a good density. So what we want to do is we want to limit the amount of scatter radiation that strikes the image receptor. So this guy named Gustav Bucky is accredited with developing the first grid, and that page number might not be completely right. But the grids help to improve the contrast by reducing scatter radiation. Unfortunately, it increases patient dose, and we'll get there later in the semester. So that's how we improved the image quality. So a big thing that you need to understand at this point is basic radiation protection. So we've got radiation protection for the patient, we've got radiation protection for the technologist or the student. So when I say technologist, just understand that I'm including students in that as well. So for the patient, what we want to do is we want to expose the patient to as little radiation as we can. So we want to keep the patient dose as low as reasonably achievable. So how do we do that? We do that with proper technical factors. So KVP and mass being our technical factors. And we'll talk extensively about those this semester and next semester as well. So KVP is the power of the X-ray beam, how likely it is to penetrate. So KVP, just relate that P to a lot of things. So potential difference, penetrating power, and that really gives us quality of the X-ray beam. The higher the KVP, the higher the quality of the X-ray beam, the more it can penetrate. Mass is just a number of electrons we send across the X-ray tube. Send across the X-ray tube, and in that it controls the number of X-rays that we create. So we want to use a proper technique. We want to use a well-filtered X-ray beam. We already talked about that. And we want to limit the beam to the anatomy of interest. So we want to collimate as tightly as possible without clipping anatomy that we need to see. So what I've seen probably in the last few years with the advent of single-size image receptors in digital imaging is a decrease in collimation. So whenever we increase collimation, that means to make the field size smaller. Decreased collimation means to make the field size larger. So what I've seen in the images that I've seen coming out of the hospitals with both students and technologists is a larger field size. And that doesn't do anything except for increase the patient's dose. So this is something you really need to focus on, and I'm going to hammer that quite a bit whenever we get into upper extremities in the next section. So our basic radiation for the patient and the public, provide shielding where appropriate. So shielding, when we're talking about shielding, what we're talking about are things like if you go to the dentist's office, they put an apron on you before they take the x-rays of your mouth. There's quite a bit of debate right now as to whether or not shielding is actually appropriate in a diagnostic setting, because what happens is that the x-rays can enter inside underneath the shielding and kind of bounce around and create more radiation exposure for the patient in the presence of shielding. And that's really kind of patient shielding. So if you're doing a KUB on a patient, that's an abdomen, or let's say a chest x-ray on a patient, you put a shield over their abdomen to protect their abdominal contents. There's some theory and also some studies that indicate that that's counterproductive, that it may increase the radiation dose. So you're going to need to follow your hospital, your institutional protocols for shielding. Protective barriers are absolutely essential. So you don't really see the protective barriers, but every x-ray room is lead lined. And you can see the lead lining in the door that goes directly into the x-ray suite. Sometimes if you're looking at the edge of the door, what you'll see is you might see just a little bit of a portion that sticks out a little bit, and that might be exposed lead, or it might not be exposed lead. It may be covered up with some sort of laminate so that you can't really see it, but that's what it is. So everything in that x-ray room is going to be either lead lined, or it's going to have enough building material to act like it's lead lined. So the floor, maybe a foot of concrete. No x-ray beam is going to get through a foot of concrete. Ceiling, excuse me, maybe the same way. So what you have is primary barriers and you have secondary barriers. A primary barrier is anything that you might point the x-ray tube at. So the floor would be a primary barrier. The wall behind the wall bucket would be a primary barrier. Where you stand when you're making your exposure is a barrier. So there's lead both in the windows, and you have to have a window so that you can keep an eye on the patient. But there is lead in that window, and it's actually, even though the window appears to be very translucent or very clear, it's pretty, whatever they put in there, be it lead or whatever else, is really pretty good at absorbing those x-rays. And the wall around the window is also going to be lead lined as well. So protective barriers, and then limit the number of repeats. So the protective barriers are for your protection, but also for protection of the general public. But you certainly want to limit the number of repeats that you have to make. Now you're a first year student. You're going to make a lot of repeats. Even technologists are going to have their fair share of repeats, but you need to approach every x-ray that you're trying to take with the care that you're trying to make it perfect. Not every x-ray is going to be perfect, but it does not mean that you should not be trying to make every x-ray perfect. So remember that the enemy of good is better. I've got a gnat. The enemy of good is better. So if you get a good x-ray, there's no reason to go back and repeat that x-ray just to make it perfect. If it includes the anatomy of interest that you need to see, it's got good contrast, it's got good density, your index number is good, everything is good, and it shows the pathology that you need to see, then don't repeat it. But if you've got significant rotation, things like that, then it probably needs to be repeated. So basic radiation protection for you as a technologist or as a student is there are three different things. One is time, one is distance, and one is shielding. So for you want to spend as little time in the x-ray suite, in the x-ray room with an energized tube as possible. It says sometimes you can't get out of the x-ray room. Sometimes you have to be in the x-ray room while the x-ray is being created, like in fluoroscopy exams. You have to be present. So what that means to you then is that you have to take other steps to make sure that you don't receive too much radiation exposure. So the next thing would be your shielding. So you want to make sure that you're wearing lead shielding. If you want to wear a thyroid shield, that's fine. If you want to wear glasses, lead-lined glasses, that's okay too. But most people just wear the lead apron. But more significantly than the lead apron is the distance that you can put between yourself and the x-ray source. And the patient is actually your x-ray source. 100% of your radiation dose as a student or radiographer should come from scatter radiation. So whenever you're doing fluoroscopy, what you should have then is 100% of your dose is coming from the scatter radiation coming off of the patient. So you want to increase your distance when you can away from the patient. And what that looks like then is that whenever you're doing a fluoro case, you don't need to be right up next to the table, right next to the patient. There are times that you need to get close to the patient and give them a pillow, give them some barium or some contrast or whatever to drink. But most of the time, you don't need to be that close to the patient, so take a step back. So this goes well beyond what you need to know right now, but there's a law that states that the intensity or the amount of electromagnetic radiation that you can receive is inversely proportional to the square of the distance between you and that source. Okay, so that's a lot of words to say this. The further you get away from the source of electromagnetic radiation, the lower your dose goes. And it works not just by doubling. In other words, if you take, let's say you're standing a foot away from the patient and you get a dose, if you increase your distance to 2 feet, that doesn't mean that your dose goes down by a factor of 2. It's inverse square law, which means as one thing goes up, another thing goes down. As distance goes up, dose goes down. So if you increase your distance from 1 foot to 2 feet, that's a factor of 2. That does not mean that your radiation dose is going to go down by 2. This is what we refer to as the inverse. As one thing goes up, another thing goes down. Square mathematically means something times itself, law. So as your distance increases from a source of electromagnetic radiation, the dose you receive from that source is going to drop by a square of the distance. So you double your distance and your dose goes down by a factor of 4. All right? So you increase your distance from 1 foot to 2 feet, your dose goes down by a factor of 4. You increase your distance from 1 foot to, instead of 2 feet, 4 feet, then your distance is going to go down by 16. So the further you can get away from the patient, I'm not advocating for you stepping all the way back up against the wall, but the further you can reasonably get away from the patient during radiation exposure, the more your dose is going to go down. I hesitate to say this because this is going to be on the internet and some radiologist or PA may pick up on this and I might get blasted for this. But the other thing is this: you're a student. You're getting $0 and you're getting radiation dose. So there's another step that you can take that combines really kind of two of these things. And that is that if you're working a fluoro case with a radiologist who's making a lot of money, or a physician's assistant or a radiologist assistant who's also making pretty good money, not radiologist money, but it's still pretty good money, then if you can back up away from the patient and then step just a little bit behind that radiologist or that PA or the RA, then they're taking the radiation dose. They have to be there anyway. They're taking the radiation dose that, and they're blocking some radiation dose from getting to you. So back away from the patient as much as you can, wear your apron and spend as little time in the x-ray suite as possible, and your radiation dose should be pretty negligible. All right, so this really kind of gets into the next chapter, but if I could direct you to your textbook, then I want to show you and talk about on page 13, numeric prefixes. And our numeric prefixes that we're going to talk about in radiology is really two things. Kilovoltage. Kilo means thousands. So I'm just going to back that up, get it off the screen. Kilo means thousands. So what we're going to use is kVp, which means we're going to use thousands of volts. So even if we're just taking an x-ray of a hand, then our voltage, the voltage or kilovoltage that we're going to use is maybe 55 to 60 kilovolts, which means 55 to 60,000 volts. Our other technical factor is mass. Mass stands for milliampere seconds. So that's just the quantity of x-rays that we create. kVp, penetrating power, potential difference. With kVp, we're going to use tens of thousands, if not 100,000 or more volts, or kilovolts would be 100 kVp. With milliamperage seconds, we're going to go in the opposite direction with it. Milliamperage, or milli, is 1/1000th. So we're going to use very high voltage, very low amperage in order to create x-rays. So then we have radiologic units that we need to talk about. So in radiologic units, these are special units that we use to describe radiation exposure of some sort. So we've got three different radiation units that we're going to use in diagnostic radiology. So in your textbook, what you probably would want to do is to mark a couple of things. So on page 13, you'll see air karma, that is kinetic energy released in matter. Air karma is the kinetic energy transferred from photons to electrons during ionization and excitation. So air karma is your unit of radiation exposure. So what that used to be is Röntgen, just like the guy who invented x-rays is William Röntgen. The Röntgen is the equivalent of air karma. We just don't use it all that much anymore. Our absorbed dose, or a rad, is the dose in tissue. So what you would want to take note of on page 13 is you see that's referred to as gray. GY equals, that means gray. So GYT is gray in tissue, but if you flip the page over, I'm sorry. Air karma is also gray, but it's gray in air. So air karma and absorbed dose are both gray. It's just where are you measuring that? Air karma is in the air, absorbed dose is in the tissue. Now if you flip over, your effective dose is what we refer to as a sievert. And it's important to note, and Amy's going to run through this next semester, but it's important to note that air karma, a unit of air karma, is equivalent to a unit of gray in a tissue, or absorbed dose, which is equivalent to the effective dose. Now your effective dose, though, is previously it was referred to as REM. So kind of like rapid eye movement, but it stands for rad equivalent man. All right. So your radiation dose reports, in a lot of cases, depending on which service you're using, but your radiation dose reports may actually come in REM. So what the sievert is occupational dose. So if you get your radiation dose report, you access that through the website, then what you may see is either sievert or REM. So they really kind of mean the same thing. The unit of measurement, Amy's going to go through next semester, that they're not exactly the same, but in a lot of cases, REM is still used. Then becquerel is the unit of radioactivity. So whenever we're talking about radioactive decay of unstable atoms, then what we're talking about is becquerel. So that really kind of brings us up to the end of the chapter. I don't think I missed anything of importance that you're going to need for the test. Going through my notes here, I think that pretty much covers it. If you have any questions, just respond below in the comment section. If this was helpful and it made sense to you, please hit the thumbs up button. If you're not one of my students and you would like to subscribe, I would appreciate that. And we'll pick up with Chapter 2 in the next recording. One thing that I am going to record is, so we have some intensifying screens in our lab, and I made some exposures on those intensifying screens so that you can kind of see what fluorescent looks like. Again, fluorescence is just light emission in response to a stimulus being X-rays. So what we used in those intensifying screens are not the barium platinum cyanide. We used all different types of substances, calcium tungstate, and a collection of 3 different types in what we refer to as rare earth screens. So what you'll see in that is a glow of rare earth screens. So I'll link also the videos that I referenced earlier in this recording in the comments section of the YouTube video. Thank you very much. Thanks for listening.